Hi everybody, Professor Burns here, and we have reached our last section for Chapter 2, which is looking at a couple different techniques we can use to solve first-order differential equations if all of the other techniques that we've learned so far will not work. So we've talked about if an equation is separable, just separate the variables. If it is linear, we can use that integrating factor technique. If it is an exact equation, we have a technique for that. If it is close to an exact equation, we can find a special integrating factor to make it exact. But what if all of those fail? What if that doesn't work? There's a few other options we have depending on the type of equation we're looking at. So we're going to go through a few examples today. Some of these can be a little tricky the first time you learn them, mostly just kind of getting used to the algebra and what to look for in each equation. So we'll go through a few examples and we'll do plenty of practice in class. Make sure your cell phone is put away and you're ready to go and take notes in your course packet. Let's just start off with looking at a type of differential equation that's called a homogeneous equation. Now, there is a test for homogeneous equations, whether they're differential equations or not, but basically the rule of thumb is if the equation can be written in the form dy dx equals some function of y over x. So in other words, some ratio of y to x becomes the argument, in other words. That means you have a homogeneous equation. And we will practice identifying these in class because it is a little tricky the first time you work with them. But one test that might help identify when you have a homogeneous equation is to make a little substitution. So I'm going to just kind of write this off to the side here. Make a substitution for x and y, replace those with zx and zy and see what happens. Let me show you what I mean. So if I have a function in terms of x and y, I'm going to write that in terms of zx and zy and then do some algebra to it. And if I can get some power of z times the original equation, that's a clue that it's a homogeneous equation. And as I said, we'll practice this, so do not stress too much about whether or not you recognize this pattern at this point, but I want to show you how that works with this first example. So if I wanted to tell if this is a homogeneous equation using this test, then what I would do is I would first rewrite it so that it's in terms of dy dx. That's the first thing I would do. So in order to do that, I'm going to divide everything by dx on both sides of the equation. Let's see what that gives us if we do that. And let me go back to my red pen here. All right, so that gives me, so the equivalent would be x minus y plus x over dy dx equals 0. Now get dy dx by itself, and I have x dy dx equals, I'm going to move the x and the y to the other side, so that gives me positive y minus x, and then divide by the x, I have dy dx equals y minus x over x. So I guess that's the first thing I would do, is rewrite it as dy dx equals some expression and then work with what you have. Now, let me get back to this little sort of mini test here. So what I would do at this point to see if it's a homogeneous equation, if you're not sure, multiply the right side by z over z. And you can do that because that's just multiplying it by 1. So that would be zy minus zx over zx. And observe that that would just be z times the original expression. What you would want to observe there is that what you have now is essentially just z times dy dx. And that's what you need in order for this test to hold up. It needs to be some power of z, in this case it's just z to the first power, times the original function, which was dy dx, or this y minus x over x expression. Okay, I don't want to get too hung up on whether or not this test makes sense to you. We'll practice this some more in class. Just take my word for it, if you're a little fuzzy here, that this is a homogeneous equation. So let's get back to what to do when we have an equation in this form. We're going to make this substitution, and we're going to let v equal y over x, and then let's see where that takes us. If we let v equal y over x. And then I'm going to rewrite that as vx equals y. Just rewrite it, move the x to the other side. So we're going to let v equal y over x, that's our substitution. And then take the derivative after you've rewritten it in this format. Take the derivative of both sides and use product rule to do that. Now I'm going to write the derivative of y first. That's dy dx. So the derivative in terms of x, of course. Derivative of y with respect to x equals, I'm using implicit differentiation and a product rule here. Derivative of the first, dv dx, times the second recopied, plus the derivative of the second, which would just be 1, times the first recopied. So dy dx, in other words, is equivalent to dv dx times x plus v. So let me go back to my equation, my differential equation, and let me rewrite it now in terms of x and v using these substitutions that we just talked about. So v is equal to y over x, meaning y equals vx, and then additionally dy dx is going to be replaced with dv dx x plus v. And I know this looks like it's more complicated, but this will get us into something that is separable, and that's our goal. So we're going to end up with, let's see, dv dx times x plus v becomes the left side of the equation. And then y becomes vx minus, I'm going to leave x as is, and I'm going to leave the other x as is. So now I have a differential equation in terms of x and v, and this is, in fact, a separable differential equation. Let's simplify a little bit so you can see what I'm talking about. The right side, notice, simplifies because those x's will reduce out. That becomes v minus 1. So now I have dv dx times x. And by the way, notice too that those v's will zero out, right? This v and this v, so those zero out. So I have dv dx times x equals negative 1. And now, if I move the dx to the other side and I divide by x, I wind up with dv equals, let's see, dx, negative 1, dx over x. And that, in fact, is a separable differential equation. Now I've separated the variables, and I can go ahead and integrate. So I have v equals negative 1 over x. The integral of that would be the natural log of x plus c. And then the last step is to replace the v. Remember, v, we want our solution to be in terms of x and y. So I'm going to replace v with what we substituted back here, which was y over x equals negative natural log absolute value of x plus c. And it's good measure to get the y by itself if that's easy to do so. So I'm going to multiply both sides by x, and I get y equals negative x times the natural log of the absolute value of x plus cx. And that would be the general solution for the differential equation. All right, let's talk about the next method, the next sort of special substitution that we're going to use, and that would be if we have a differential equation in this format, where we have dy dx equals some function of ax plus by. So like in the last example, we had some function of y over x, where that was our argument. Now we want something where we have an argument that's linear, ax plus by. And if that's the case, we're going to let z equal that argument, and then we'll be able to separate the variables. So it may take a little bit of creativity here to see the substitutions with some of these, but what I hope you observe in this example is that I have a linear function in terms like ax plus by, linear function, y minus x twice, that appears twice. So if we think about how do we rewrite so that this is a function, or so that your argument, I like that term, your argument is going to turn into ax plus by, so instead of y minus x, I'm going to write it as x minus y. Let's do it that way. And so how can we get that out of this expression? Well, I'm going to write these first two terms as negative x minus y, and then I've got a minus 1 after that, plus, and then I'm going to do a little box here, and I'm going to write the second expression as x minus y plus 2, and all of that raised to the negative first power. So I didn't do any heavy algebra here to manipulate or multiply by anything. All I kind of did was rearranged so that I've got this x minus y expression that can now be replaced with that z substitution. So I'm going to let z equal x minus y. So similar to the last example, I'm doing a change of variables here. I'm letting z equal x minus y. Then I'm going to take the derivative of this in terms of x. So dz dx becomes 1 minus dy dx. And I want to rewrite my original differential equation in terms of z and x. So I'm going to solve this little equation here for dy dx. So that means I have dy dx equals 1 minus dz dx. So now let me go ahead and rewrite my differential equation using those substitutions. So these x minus y expressions are going to turn into a z, and then the dy dx expression is now going to turn into this 1 minus dz dx. So we're going to end up with 1 minus dz dx equals negative z minus 1 plus z plus 2 to the negative first power. So I'm just making those substitutions into my differential equation. So now I have a differential equation that's in terms of z and x. I'm going to do some rearranging here. I'm going to get the dz dx by itself. So I'm going to subtract the 1 and multiply through by negative 1. So in doing that, that gives me, let's see, I'm going to get z plus 2. Pause the video, please, and go through and do the algebra. Solve for dz dx and combine like terms, and make sure you see that you get the same thing that I have here. So this z plus 2 to the negative first, I'm writing it as 1 over. And then when you combine those two and get a common denominator, you wind up with z plus 2 to the second minus 1 all over z plus 2. So that is the differential equation that I'm going to work with. And that might seem like, wow, that's a lot of steps to get there, but the good news is this gives us something that is now a separable differential equation. I can go ahead and just multiply the dx to the other side and then use the reciprocal to get all of these z terms to the left side with the dz. So in doing that, I'm going to have z plus 2 over z plus 2 squared minus 1 dz equals simply just dx on the other side. And this maybe doesn't look as pretty as you might expect it at first glance, but this is something that we can integrate actually pretty easily, because if you distribute the z plus 2 squared in this denominator, you end up getting z squared, I'll put this in parentheses, z squared plus 4z plus 3, and then you can use a u substitution and integrate this. I'm going to skip the details for now, but I do want you to pause the video, and I mean it. Don't just write this down. Pause the video, do the u substitution, old-fashioned u substitution, let u equal this denominator, and you will see that the derivative will contain the z plus 2 that you need in the numerator. So when you integrate that, you wind up with 1/2 times the natural log of u, which is going to be this z plus, and I'm just going to write it, z squared plus 4z plus 3 expression equals, on the other side, your antiderivative is going to be x plus c. And then, of course, you need to replace the z with what it was equivalent to, so that gives me 1/2 times the natural log of z, which was what was z equal to again? It was equal to y minus x. So that becomes y minus x to the second plus 4 times y minus x plus 3 equals x plus c. And I'm going to stop there because I'm running short on time in this video. I want you to watch the next video to see the last example, but this is an implicit version of the solution to that differential equation. So I'll see you in the next video.